Hey all you cool cats and kittens, welcome back to another episode of Machining Solutions. Today what we're going to be doing is discussing part 2 of a two-part topic, and that's how to properly calculate speeds and feeds for a milling operation. So we have a few different holder options here. We'll go briefly over why we're going to choose which holder we are. We've got an FTT HFP mill. I'll leave it up to the imagination as to what that acronym stands for. We've got some 4140 alloy steel in our Haas VF2. Let's make some chips. So as you can see, we have 3 different options for tool holders here, and I just want to briefly discuss a few of the features and why I'm going to choose the one that I am. So on this side here, we have the ER32 just standard holder. This is really ideally suited for job shops that just need to clamp a range of different tools. Need to get something done, just something very general purpose. Ideally suited for drilling operations, reaming, some light milling, things of that nature. We then have the NT Tool Mavius holder. This again is a very general purpose tool, ideally suited for job shop type operations, though it does have some tighter tolerances than our normal general purpose ER holder, so it could be a good second choice for us here, but still utilizing that collet. And next up we have the NT Tool hydraulic holder, and this is going to be our winner for this operation. So a few key differences. This holder does not use collets. It actually is a direct chucking holder. You'll also notice that rather than utilizing tapered collets like our collet holders, this actually just has a straight hole for the shank of the tool to be received. So we insert our tool, and rather than having collets that are going to compress on the tool, we have hydraulic chambers within this holder. When we tighten our set screw down, we're actually creating hydraulic pressure in those chambers, and in turn, that is going to clamp on a very thin sleeve on the inside of this bore, and it's going to clamp evenly on this tool. This is ideal for minimizing runout, high clamping forces, and also since we have a liquid chamber in this holder filled with hydraulic oil, it's going to allow some dampening. This is really great for milling operations that are susceptible to chatter because it's actually going to absorb some of that vibration, so really ideally suited for milling operations. Also a great choice for high precision drilling and reaming operations, but in this case we're going to use our 5/8 end mill and we're going to get to work. So the next thing we're going to do is we're going to pull up our speed and feed calculator spreadsheet, and we're going to select all of our parameters so it can give us our ideal starting parameters. So we're utilizing an FTT HFP 4-flute end mill. We're machining 4140 alloy steel. We have a 5/8 tool diameter. Our machine's maximum RPM is 10,000, and we are performing a side milling operation. This in turn gives us our ideal cutting conditions of 2750 RPM, 3 thou 7/10 inch per tooth, 40.7 inches per minute, a radial step over of 30%, which equates to 188 thousandths, and an axial step down of 938 thousandths. You'll see over on the right hand side here we have an adjusted high-speed machining parameters table. And what this is going to account for is if we reduce our radial step over percentage, we will be utilizing a phenomenon called chip thinning. So radial chip thinning refers to that if you decrease your radial step over, you will also be decreasing your chip thickness. End mills are designed to machine and mill a certain chip thickness for each material, so we want to keep that leveled. And what we'll do is we'll increase our inch per tooth to maintain the same chip thickness. We're also going to be generating less heat, so we're able to increase our surface feet per minute, or RPM. So let's say for an example we wanted to use a 15% radial step over. Now in turn it's going to tell us that we are able to utilize 4400 RPM, 4 thousandths and 7/10 inch per tooth, so 82.7 inches per minute, a slight bump in our feed rate, will cut our radial step over in half down to 94 thousandths. So we're going to be removing a little bit more material in the same given time, but we also are going to be stressing out our system a lot less. We're going to have less tool deflection. We're going to have less susception to chatter or high torque on our spindle. We're going to have less wear and tear on our machine. Ultimately, at the end of the day, we're going to get better tool life, better part quality by utilizing these high-speed machining parameters, and we'll also increase our material removal rate slightly as well. All right, let's make our first pass. So this is going to be 2750 RPM, 40.7 inches per minute, and we're going to be taking 30 thousandths radial step over and 938 thousandths axial step down. Let's see what happens. Next up, we'll do a 15% radial step over. We'll increase those RPMs to 4,400 and our feed rate to 82. And lastly here, let's take one final pass at 8% radial step over, 5170 RPM, and 130 inches per minute. Once again, perfect parameters straight out of the calculator. We're high-speed machining. Thank you guys so much for watching. I hope this video brought you value and that you saw how my speed and feed calculator can help you at least get close with your speeds and feeds. If you have any questions on how NT Tools hydraulic holders can help, or FTT's high performance end mills can help you with your applications, reach out. I'm going to put a download link to the speed and feed calculator as well as my contact information in the comments section below. Until next time, let's power down, stay safe out there.